Hi Ethene, and welcome to the video on alkenes. So again, this stress about this idea of the letter, changing a single letter will change the meaning chemically of the compound. Success criteria to look at is stating the definition of homologous series, referring to alkenes, stating the general formula of the alkene homologous series, naming and drawing the linear alkenes for up to 5 carbon atoms, naming and drawing branched alkenes with up to 4 carbon atoms. We've seen this idea of homologous series before, remembering that homo means the same, so there's something about it in which is the same. Series is a family of hydrocarbons, each have similar chemical and physical properties. Each subsequent member differs by a CH2. So the definition of homologous series is the same for any homologous series when referring to hydrocarbons. In reference to alkenes, is that an alkene is what's called an unsaturated hydrocarbon. Remembering that hydrocarbon is something which is predominantly composed of hydrogen and carbon atoms together. This means they contain less than the maximum number of hydrogens attached as possible. Alkenes, therefore, must contain at least one carbon-to-carbon double bond. So we should see this appearing in alkenes. The general formula for alkenes is CnH2n. So we can see that we've got 2 less hydrogens in the general formula compared to alkanes. One way to remember the name alkene is the fact that alkene has 2 E's. So if we remember that it's got 2 E's, then we must know then an alkene must have a double bond. To extend from this idea, we can have multiple hydrogen bonds within a structure, and for every additional double bond present, we lose a further 2 hydrogens. This general formula is for only when we have one double bond present in the compound. The first member of the alkene family is ethene. There's no such thing as methane. It doesn't make logical sense because if we only have one carbon, it can't be double bonded with another carbon. So our first member of the alkene is ethene, remembering that eth is the prefix for 2 carbon atoms. Following that general formula, CnH2n, 2 lots of 2 gives us our 4 in our molecular formula. Semi-structure, we can see CH2, CH2. This is where the double bond would be implied, knowing our chemistry that carbons must contain 4 bonds, and we can often represent it where the double bond is labelled explicitly. In terms of our, in terms of our structural formula, we can see that each carbon atom has 4 bonds in total, and hydrogens coming off there. Common mistake is to represent it like as if it was ethane with the double bond. But again, this would imply that there would be 5 bonds around each of those carbons. So keep that in mind. Our second member, but our carbon length of 3 in our carbon chains is propene. Remember that prop has the letter R in it, so prop refers to 3 carbon atoms. CnH2n, if n equals 3, 2 lots of 3 gives us our 6 hydrogens. If we look at that, CH2, CH, CH3, or if I'm explicitly showing the double bond there, it is present. So we can see here in our structural formula. Now up here, I'll show you that it's okay if we represent propene in a flattened sense rather than this more bent structure, right? So we can represent it like that, but a common mistake is putting an additional hydrogen here, right? So we want to ensure that around any given carbon atom, we don't have more than 4 bonds. So we can see I've got 4 around this first carbon, 1, 2, 3, 4 bonds around the second carbon, 1, 2, 3, 4 single bonds around that third carbon. Butene, remember that Butte is 4 carbon atoms. 4 lots of 2 gives us 8. Now, 2 different semi or condensed structural formulas present. And there's our structural formula. Again, I can represent this in a more flat manner, which would be perfectly okay. Again, as I highlighted before, just making sure you're not adding that extra hydrogen on that mid-carbon there. Just pointing that out as a common mistake. So either of those is acceptable. 5, pentene, remembering that pent is 5 carbon atoms. 5 lots of 2 gives us 10. Again, just stressing that idea that we can represent it in that flattened manner. 2 off that one, only a single carbon there, and filling in the remaining hydrogen atoms. Other common mistakes is having every carbon-to-carbon bond as a double, but that's not a general alkene. A general alkene only has the 1 double bond present. Recall this idea about isomers has a same molecular formula, but a different structure. In a difference to structural diagrams, or a different type of structural diagrams, is that we can change the position of a double bond. So like with branches, a number is often used to describe the location in which the double bond comes off. There's only one isomer of ethene and propene because there's no other way that I can represent it. So there's ethene, here's propene, and although it appears that I could represent it like this, and from a flat perspective, these two look different, but they're actually exactly the same. And I'll switch to show you an example of this. So here's ethene. If I go to now add an additional carbon, I'll remove that hydrogen, clean that structure, and here's our propene molecule, and represent that in 3 dimensions. Okay, so notice how when I've gone to 3 dimensions, the double bond appears on the right-hand side. So if I rotate this around, we can see that I get that same structure back. So whether that double bond is represented on the right or the left-hand side, it actually is the same molecule presented. So when we go to butene, there's 3 different possible structures. The first 2 is the same linear isomer where we change the position of that double bond. So just representing it in that flat form, omitting the hydrogens for simplicity, or our butene would be representing something like that. And just to show that these are different, we can look at this from, again, in a 3-dimensional sense. Let's clean that structure. So this would be an example of butene, and I'll show you that in 3 dimensions. So we can see, looks something like that. And if we then want to have a look at butene, I'm going to join that up, add an additional bond there, to remove that bond, to clean that up, remove that extra carbon, clean up those structures. So we can see side by side how these are different structures. Look at that in 3 dimensions. So we can see here, let's zoom out and show you that they are rather different. So we can see that in butene we've got 2 CH3 groups at the terminating carbons. In our butene, we only have a CH2 at the terminating at one end and a CH3 terminating at the other. So there's one example of showing you how they're different. We also have one in which it's got the double bond and a branch. So the branch here, if I want to draw this in a flat manner, it looks something like that. Okay, so again, notice there's no hydrogens attached to this carbon here, and again emitting hydrogens to make that more straightforward. We can see that this will have a propene backbone. You could also draw it like this. There's a propene backbone with a methyl group coming off that second carbon. An extension is looking at longer and longer hydrocarbons. So we have 5 different isomers of pentene. We can either shift that double bond across. Notice how there's no such thing as pent3ene. So the number is represented of which carbon the double bond starts from. So I'll show you the reason why we don't have pent3ene. So let's represent this as if it was pent3ene. So I'm going to add in an extra bond present between these 2 carbons. So I've got this additional bond between the 3rd and the 4th carbon here. Let's clean that structure. 2 dimensions to 3 dimensions. Here's our apparently pent3ene, but really, remember we're drawing these molecules flattened. They're 3-dimensional molecules, but we're drawing them in a flat manner. So that's pent2, pent3. So in reality, we're counting from the end closest to that functional group or that double bond. So pent2ene is the same as pent3ene. So pent3ene would be the inappropriate naming of that structure. And there's our other possible isomers. 2-methyl-butanene, so that methyl group coming off the second carbon. Other structures, 3-methyl-butanene, right? So the double bond takes the priority in terms of the numbering. So the number 1 carbon is here, right? And we also have 2-methyl-butanene. So we have a branched and a double bond coming off that second carbon. We wouldn't have 3-methyl-butanene because we're wanting to count closest to that end. Further extension is called geometric isomers. And because we cannot have free rotation around a double bond, we can have representations whereby they're ever so slightly different properties. So but2ene, there's actually 2 different possible representations. In year 10, not expecting you to know this difference. But notice how cis means on the same side, and it looks a bit like a C. So there's my cis, and this looks a bit like a T. Okay, so there's my trans, which means across from forms. Not all alkenes also have cis or trans forms. So if we've got the same things attached to any given carbon, so notice I've got 2 sort of methyl coming off this carbon, 2 hydrogens coming off that, that's neither cis or trans. So that is simply methyl propane. Success criteria. Homologous here is referring to alkenes, double bond, unsaturated family of hydrocarbons with similar chemical and physical properties. Each member differs by a CH2. General formula, CnH2n. Name and draw the linear alkenes up to 5 carbon atoms. Ethene is our first. Propene, butene, pentene. Name and draw branched alkenes with up to 4 carbon atoms. We've got those 3 different isomers for butene, only 1 isomer for both ethene and propene.